You know, for centuries, there's been this one type of math problem that has stumped some of the greatest minds out there. We're talking about finding the exact answer to these super complex equations, high-degree polynomials. Most of the time, we have to settle for close enough. But what if close enough just isn't good enough anymore? Today, we are diving into a method that claims to nail down the precise symbolic answer every single time.
So here's our game plan. We'll start with this old-school math problem to really set the stage. Then we're going to introduce a really powerful new tool called Ezouidi's theorem. We'll even put it to the test on a tough fifth-degree polynomial and watch its recursive magic unfold. Finally, we'll talk about what it really means to jump from just approximating to achieving absolute precision.
All right, so what is this puzzle that's been around for so long? Let's take a look at the actual challenge we're up against.
Okay, here it is, a fifth-degree polynomial. Now, if someone asked you to solve for x, where would you even start? Seriously. Most methods are just going to spit out an approximation. Yeah, that's pretty close kind of answer. But we're not hunting for close. We want the exact solution. And that, right there, is the heart of the problem. This really shows you the two different worlds of problem solving. Over on the left, you've got the classical way of doing things. It's all about numerical approximations, which means you're always running the risk of tiny rounding errors. You get close, but you're never perfectly there. But on the right, that's the promise of this new theorem, to calculate the exact symbolic root. It completely avoids those errors and gives you a perfectly precise solution. And this is a really bold claim. I mean, this method is directly challenging some very established mathematics, specifically something called Abel's impossibility theorem. And that's a famous proof that basically says there's no general one-size-fits-all formula for finding the roots of polynomials that are degree 5 or higher. And yet this new approach is saying, yeah, I can find those exact solutions anyway. That suggests a pretty fundamental shift in how we could solve these problems.
So, what exactly is this new approach that's making such a huge claim? Well, let's meet the star of our show, Ezouidi's theorem.
Think of this theorem as a whole new roadmap. It's a very structured process that takes a complex polynomial and just dismantles it piece by piece. The secret sauce here is that it's recursive, which means it takes the answer from step 1 and plugs it into step 2, then takes that result and uses it to solve step 3. It just builds on itself, step by step, until it gets to the final exact answer.
Okay, theory is great and all, but let's actually see this thing in action. We're going back to our fifth-degree polynomial, and we're going to apply this new method step by step.
Our process is pretty straightforward. First, we'll look at the core formula. Don't worry, we're focusing on the concept, not a bunch of heavy calculations. Then, we'll break down its key parts. And finally, we'll watch that recursive process do its thing. Okay, here it is, the formula at the heart of the theorem. Whoa! I know what you're thinking. That looks intense. But we are not going to solve this by hand. The real goal here is just to understand how this engine works. The key thing to notice is how it systematically combines numbers from our original polynomial with the results from previous steps to march towards a solution. Let's break this down real quick. The C terms, they're basically just mathematical adjusters. The L terms, those are the actual numbers from our original equation, you know, the 5s and the 10s. And the most important part is that S term. That's the recursive piece. It literally tells the formula, hey, use the result we got from the last step to solve this current one.
All right, with those parts in mind, let's see how the calculation actually unfolds. This is where the magic of that recursive process really starts to shine.
So the whole process kicks off at step 0, where this variable k equals 0. The theorem grabs the coefficients from our polynomial and plugs them into the formula to calculate the very first symbolic coefficient.
And what's the first result? After all that complexity, it's just 0. A remarkably simple answer. But hey, is that just a fluke? Let's move on to the next step and see.
Now we're on to step 2, where k equals 1. The theorem does the whole thing all over again, but this time it takes that first result, 0, and feeds it back into the formula. So what happens now? You guessed it, 0, again. Okay, now we're definitely seeing a pattern emerge here. It's like the theorem is systematically just canceling out all the complexity in the polynomial.
So, the source material shows this process repeating for the next 3 steps, for k equals 2, 3, and 4. The process is exactly the same, and guess what? The result is the same every single time, 0. The theorem just methodically chugs along until all the symbolic coefficients are found. So, we've run all these calculations, and every single time the result is 0. What on earth does it actually mean for our problem? Well, this is the payoff.
This is where it all comes together.
This table lays it all out crystal clear. Every single symbolic coefficient that the theorem calculated from the very first step to the very last, it all came out to 0. This is not a coincidence. This is the solution revealing itself through the process.
And here's what that really means. When all of these new coefficients turn out to be 0, the original polynomial basically just collapses on itself. All that complexity just vanishes, and it leaves behind only the core answer, the exact root of the equation.
And boom, here's the exact solution. The polynomial has one root, x equals -1, with what's called a multiplicity of 5, which just means the same answer is found 5 times. This is not an approximation. It's a precise, definitive solution derived directly from the theorem.
Look, this is way bigger than just solving one equation. This result points to a fundamental shift in how we can approach these kinds of massive mathematical challenges.
As the source material puts it, this method provides precise, solvable roots for polynomials once deemed unsolvable. That says it all, doesn't it? It's not just about getting a slightly better answer. It's about finding the right answer and moving us out of the world of close enough and into the world of absolute precision.
It really makes you wonder. If a math problem that stood for centuries can be unlocked with a totally fresh approach, what other unsolvable problems out there, in science, in technology, in medicine, are just waiting for the right person to come along and look at them from a brand new angle?